So now we're going to turn to Chapter 9, Conceptual Knowledge. So this is basically us taking a look at how does your mind organize the things that you remember. So all of the things that you learn, all of the ideas that you have, all of the stuff that you have stored away in your knowledge base, in your, for example, semantic memory, how is that actually structured? How is it organized? And what implications does that have for behavior and cognition? So we're going to talk first about the basic idea of a semantic network. And then we're going to take a look at Collins and Killian's hierarchical model. And then we're going to take a look at Collins and Loftus, her of the do you remember when you got lost at the mall experiment? Collins and Loftus's spreading activation model. And then we'll look at CogLab number 10. Hopefully have some time for a little bit of a discussion, and I'll leave you with a little thought project when we finish today. All right, so if you know who this is, it's because somewhere in your semantic network, in your conceptual knowledge network, you have a piece of information that says, oh, that is Abraham Lincoln. And if you know that Abraham Lincoln was the 16th president of the United States, and he served until his assassination in 1865, that all needs to be represented somehow in your conceptual knowledge. If you further know that he delivered the Gettysburg Address, that is also somewhere in your semantic knowledge. So this is very interesting. This is one of only 2 verified photos of Abraham Lincoln. So he is right there. So we can zoom in on that. And that is him at the Gettysburg Address. So this is all information that you might have about Abraham Lincoln. The fact that you have it, the fact that it's stored somewhere, means that it needs to be stored somehow. And this is all about how might that information be stored. So the first thing that we're going to think about is just the basic idea of a semantic network. The basic idea of how are your semantic knowledge items organized in your mind. So the semantic knowledge that you have, it can be thought of as a list of propositions. So the idea that somebody could come up to you and say, hey, can you write out everything that you know? And if you actually could accomplish that, that would be a list of propositions that represented your semantic knowledge. So somewhere in your semantic knowledge, you might have a proposition that looks like this. Lincoln, who was president of the United States, delivered the Gettysburg Address. So how would that statement be organized or how could that statement be represented in a semantic network? So we got the statement. So propositions in this semantic network, they are represented as nodes, and these are nodes. Nodes are the relations between concepts and the arguments that those concepts have. And then we also have links, and the links are the connections between the various nodes. So let's take a look at how Lincoln, who was president of the United States, delivered the Gettysburg Address, might be represented in a semantic network. So we have the nodes, we have relations, and we have arguments, and then we have links. So in this case, we'll start off with a link. So these blue dots, they're going to represent the links. And the links are going to connect different nodes. And the nodes are either going to be relations or they're going to be the arguments of those relations. So the first one we have is a relation. And we have the relation of agent, right? So agent means somebody who is doing something, right? So that's the relation, somebody who is doing something. And then what is the argument that is associated with that relation? Well, in this semantic network, it would be Lincoln. So right now we have represented that Lincoln is doing something, right? So that is now represented in this semantic network. And that link, that blue dot, can have other relations and other arguments connected to it. So it could have the argument of relation. So we have the argument of, we have the relation of relation, and then the argument is president of. So now we have Lincoln doing something, and it's related to him being president of. So now we need more representation in this semantic network. So we have another connection to an argument, and that argument is now, we have another connection to a relation, and that relation is object, and the argument of that object is United States. So at this point, we have Lincoln, president of United States. We have now represented Lincoln, who was president of the United States, in this semantic network. We have more information that needs to be linked in there. So we have another link, and this link is again connected to the relation of agent, and that agent is now connected to Lincoln. So now we can add more semantic information about this individual Lincoln. And we keep building our semantic network with the relation of delivered. And then we have, again, the relation of object, and the object is Gettysburg Address. So now we have Lincoln was the person doing, Lincoln was the agent that did something. What was it? Delivered. And what was it that he delivered? The object, the Gettysburg Address. So now we have Lincoln, who was president of the United States. Lincoln delivered the Gettysburg Address. We have that information represented in this semantic network. So this is a hypothetical organizational structure. And it basically shows how these ideas are all related together. Now, let's say that we could go into this semantic network and we can do some inception level stuff. And we can go in there and we can start moving things around, and we can start changing information, and we can start playing with parts of this semantic network in that sort of inception idea of planting other information. So what might we be able to do? Well, let's say that we were able to get in there and we were able to go to Lincoln. We went to that argument, Lincoln, and we were able to switch it out. Not for Lincoln, but now we were able to switch it out for Bill Gates. Our knowledge now would change from Lincoln, who was president of the United States, delivered the Gettysburg Address, to Bill Gates, who was president of the United States, delivered the Gettysburg Address. And if we could go in there again and do some more inception, and we take the United States, the object United States, and we say we're going to switch that out with Microsoft. Now we have the information. Bill Gates, who was president of Microsoft, delivered the Gettysburg Address. Yep. Yes. Yes. If we, in a semantic network like this, literally everything that you knew would be linked, everything you knew about Lincoln would be linked to Lincoln. So if you got rid of the node that was Lincoln and you switched it out for somebody else, then you would totally forget who Lincoln was, and everything that Lincoln did and everything that you knew about him would get replaced with this new individual. All right, and let's say that we kept going, and instead of the relation delivered, we changed that to programmed. So we got Bill Gates, who was president of Microsoft, programmed the Gettysburg Address, and then you can probably see where this is going. We go in one more time, we incept it one more time. We change Gettysburg Address to Windows, and now we have Bill Gates, who was president of Microsoft, programmed the Windows. Should have got rid of the Windows, but anyways, programmed the Windows. So in this case, you can see how two very different semantic ideas, two very different semantic pieces of knowledge are basically represented in much the same structure in this semantic network. And if you lose certain ideas in this kind of idea of a semantic network, they would be changed across your entire knowledge of that. So if you switched out Lincoln for Bill Gates, everything that you knew about Lincoln, you would now attribute to Bill Gates. Mm-hmm. Oh, yeah. Yeah, absolutely. I mean, if you learn about a new person, you're basically creating all these new nodes. So in this formulation of it, at some point you would have, so they would be linked, but they would be linked by their shared concepts. Yeah. So Bill Gates is president of Microsoft. Steve Jobs, president of Apple. In that case, both those president ofs would be linked because that idea, that conceptual idea, would be the same idea. So they're linked in this semantic network through president of, which is why you would be able to say, well, can you list all the presidents of major corporations? and you would be able to go to that president of node and then go to agent and say, oh, one of the agents linked is Bill Gates. Another one of the agents linked is Steve Jobs. And that's how they would be kind of related to each other. Same thing with president of the United States. Anybody that you learned as the president of the United States, you would somehow attach to that concept in that node, and that would represent your knowledge of them. All right, so that's a general idea of a semantic network. General idea that you can be connected to different nodes, different relations, and that's how our knowledge is represented. So given that that's a potential of how we organize our knowledge, then we start asking as psychologists, well, how does this semantic network actually organize? How is it actually put together in our minds? So this is one possible way of doing it. So now let's run some experiments, let's do some research, let's come up with some models that try to explain how we actually represent our semantic knowledge in a semantic network. So we're going to start off with Collin and Killian's hierarchical model. So in this one, it basically says that you have your knowledge organized in hierarchies, and those hierarchies have links to subsets, sub-hierarchies, and links to super hierarchies, and that's how your knowledge is organized. So for example, you might have the node of animal, and that node would have everything that you know about animals linked to it. So it would have things like has skin, so animals have skin, animals can move around, animals eat, animals breathe. So you would have all those features linked to that node that says animal. Animal would then be in this hierarchy linked to a lower level that now has the different types of animals. So animal would be linked to bird. And you would have the information, the features that are common to birds linked to that bird. So things like has wings, things like can fly, things like has feathers. And then below that level in this hierarchy, you would then have specific birds. So things like canaries and ostriches, and you would have canary can sing is yellow, and you would have ostrich is tall, ostrich can't fly, ostrich has long, thin legs. And then going off that top level of animal, you would have basically every other type of animal that you know. So we would have the node for fish, and fish would have information like has fins, can swim, has gills. And then you would have information for specific fish like sharks and salmon. So sharks can bite, are dangerous. Salmon is pink, is edible. So the idea is that our knowledge is organized in this type of a hierarchical structure where we have categories and subcategories that allow us to kind of organize all of our knowledge in this particular kind of a structure. All right, so this was Collin and Killian's model of conceptual knowledge. It is a propositional network where basically it's that idea of a semantic network where your knowledge is represented as propositions, as statements about what you know. And they made a couple assumptions about how this model would work. So assumption number one is that retrieving a property takes time. So when you go to bird, retrieving the idea that a bird has wings, that takes a certain amount of time. When you go to shark, retrieving the idea that shark is dangerous, that takes a little bit of time. So retrieving a property actually takes time. And then also traversing the hierarchy takes time. So if you're thinking about canaries and you have to start thinking about birds in general, well, then it takes time to go from the canary node to the bird node. And if you're thinking about birds, but you want to start thinking about animals, it takes time to go from the bird level to the animal level. So traversing that hierarchy takes some time. All right, assumption number two is that these times to retrieve properties or traverse a hierarchy, they are additive when one step is dependent on the completion of the other. So if it takes time for you to go from canary to bird, and it takes time for you to go from bird to has feathers, then it's going to take additive. Those two times are going to be added if you go from canary to thinking about do birds in general have feathers. So moving through this hierarchy is much like moving through a map. Times are additive. When you have to go to one location and then go to another location, those times add up. All right, and then finally, assumption number 3, the time to retrieve a property is independent of the hierarchy level. So if you're being asked questions about animals, does an animal have skin? Can an animal move around? Your time that it's going to take you to retrieve those properties and answer that question will be the same time that it's going to take you to answer, is an ostrich tall? Can an ostrich fly? So it doesn't matter if you're at a super level, the top level, answering questions about animals. It doesn't matter if you're at the bottom level, answering questions about canaries. Doesn't matter if you're in the middle, answering questions about birds. The time to retrieve a property is going to be independent of the level of the hierarchy that you're in. So they propose this theory, this model of how our memory is, how our semantic knowledge is organized. So what would actually happen if our knowledge was organized in this way? Well, if this was the way that our knowledge was organized, then we would have different reaction times to verify different types of sentences. And those different reaction times would depend on how many hierarchies needed to be traversed in order to answer your question. So depending upon how many hierarchies need to be traveled in order to verify a sentence, it should take longer depending upon more hierarchies needing to be covered. So let me give you a better example of that than that abstract explanation. So they had things like superset sentences, and these were sentences that could be answered by going up or down levels of the hierarchy. So we have things like a canary is a canary. How long would it be if I told you you need to answer as quickly as you can? Is this true or is this false? A canary is a canary. It's going to take you some time, milliseconds, but it's going to take you a little bit of time to say, oh yeah, canary is a canary, of course. The idea is that you start off at this level in the hierarchy and you stay at that level of the hierarchy, and that's the time that it takes you to answer a canary as a canary. Well, what about a canary as a bird? Well, according to Collin and Killian's hierarchical model, that should take longer. Because if you need to answer a canary as a bird, you start off at canary, you got to move up to where it says bird, and that takes some time. So to verify a canary as a bird, if this model is correct, should take you longer than verifying a canary as a canary. And then we have superset sentences S2, which require traversing 2 levels of this hierarchy. So if you are asked, hey, is a canary an animal? Well, you got to go from canary up to bird, that's going to take some time, and then from bird up to animal, that's going to take more time. So that type of a sentence should take the longest to figure out if it's true or not. So they had superset sentences where all you needed to do was traverse the hierarchy, just go up a level or down the level. And then they had property sentences. And in the property sentences, these required you to also access a property at a particular level. So they had property 0 sentences where you didn't have to go up a level at all. So is a canary yellow? All you need to do is stay at that node for canary and access is yellow. If you're going to answer the question, does a canary have feathers? You got to go from canary up to bird. That's going to take some time. And then you access has feathers. That's also going to take some time. And then finally, you can ask, does a canary have skin? That means you start at canary, you go up to bird, and from bird, you go up to animal. That takes more time. And then from animal, you access has skin. So that would take, in this case, the longest time to verify. So let's take a look at what they actually found in terms of what would happen if our conceptual knowledge was organized this way. And did they actually find different reaction times to verify those different sentences? So they had a large selection of sentences that they used. So an oak has acorns, ping pong has baskets, lemonade is alcoholic, root beer is a soft drink. They had all of these different types of sentences, and they were organized on how many levels do you have to traverse, and do you have to access a property, or is it just traversing the levels? So let's take a look at what they found. All right, so here on the x-axis at the bottom there, we have the level of the true sentences. We're only going to be looking at true sentences. So we're going to have the levels of true sentences. So 0 level sentences, 1 level sentences, 2 level sentences, depending upon how many hierarchies they needed to traverse. And then on the y-axis there, we have mean reaction time in milliseconds. So it starts at about 900 milliseconds. So it starts at about a second in order to say, yes, that is true, all the way up to about a second and a half. So let's see what happened. So we'll start off with a canary can sing. This is a property sentence, and all you need to do is you stay at the level that you're at, you stay at that canary level, and you access a property, can sing. Next level up, a canary can fly. In that case, you got to go up a level to where bird is, and then access that property, and as it turns out, that takes longer. So the higher the line is, the longer it took people to verify that sentence. And if you take a look at a 2-level property sentence, a canary has skin, that takes even longer. And very, very cleanly, this is some of the cleanest data I've ever seen, that's a straight line. Meaning to go from a canary to can sing to a canary can fly, to go up 1 level takes a certain amount of time, takes the same amount of time to go up from that 2nd level to the 3rd level. Super, super straight line. What about the ones where you're just going up levels? You're not actually accessing properties. Well, a canary is a canary. That takes about a second for people to get that information out and say, yep, canary is a canary. We go up 1 level, a canary is a bird. That takes a certain amount of time. To go up 2 levels, a canary is an animal. That takes even longer. Almost a straight line in this case. So as you can see, going up a hierarchy, going from 0 levels to traversing 1 level to traversing 2 level, the more hierarchies you go up, the longer it takes you to get to that top level. So what do these reaction times tell us about traveling the hierarchy? Well, what it tells us is that it takes about 75 milliseconds to travel up a level. So it takes about 75 milliseconds to go up each level. So if you have to go up no levels, 0 milliseconds. If you have to go up 1 level, 75 milliseconds. If you got to go up 2 levels, 150 milliseconds. That's about how long it takes you to travel up a different level. What about how long does it take you to access a property? Because what they said was that accessing a property is independent of the level that you're at. If you're at the top level or if you're at the bottom level, accessing a property should take you the same amount of time. Is that what they actually found? Well, if you compare how long it took you to verify a canary is a canary with how long it took you to verify a canary can sing, we can say we know that that's the difference there is how long it takes you to verify a property. Because a canary is a canary doesn't require a property. A canary can sing requires a property. So that difference in reaction time is how long does it take you to access a property. And as you can see, for each level, these 2 lines are basically parallel. It takes the same amount of time to access a property when you're at, regardless of the level of the hierarchy that you're at. So it looks like it takes about 75 milliseconds to travel up a level. It takes about 225 milliseconds to retrieve a property. So very strong evidence in this case for the Collins and Killian's hierarchical model. All right, so as it turns out, very strong evidence for the hierarchical model, but there were some intractable problems with the hierarchical model. There were some problems about the way that we actually behave that just could not be explained with Collins and Killian's hierarchical model. So what are some of these problems? Well, one of these problems has to do with the typicality effect. And the typicality effect is that it's a finding, it's a phenomenon, it's what we actually do. Things that are more typical of a certain category, members that are more typical of a certain category can be verified much more quickly than ones that are not typical. So one of the classic examples of this is if I asked you, is a robin a bird? You would be very, very quick. Importantly, you would be faster than if I asked you if a penguin was a bird. So robins, highly typical of birds. So if you ask most people to just name a bird, most people will have robin in their top 10 list. However, very few people would have penguin in their top 10 list. So penguin is not typical. Collins and Killian's model would predict that does not matter because going up and down a hierarchy takes the same amount of time. Accessing a property takes the same amount of time. And yet we are much quicker at answering, is a robin a bird, than we are answering, is a penguin a bird. So that was one of the first stumbling blocks. Another stumbling block was the fact that structures are not perfectly hierarchical. So the classic examples of this is that if you ask somebody, is a dog an animal? They will be much quicker at answering, is a dog an animal, than is a dog a mammal. And that does not make sense according to Collins and Killian's hierarchical model, because is a dog a mammal requires just one level to be traversed. Is a dog an animal requires two. So seems like there's not perfect hierarchical structures. The typicality effect is something that couldn't be addressed in this type of a model. So Collins went on to do more research on this and paired with Loftus, and they came up with what is known as the spreading activation model. And this model was proposed in 1975. It was a revision of the hierarchical model. And the new features was first that it was not strictly hierarchical. So it didn't have levels in the way that Collins and Killian's model had those hierarchical levels. Links between concepts now had different travel times. So not all links were equal. Links between different concepts and links between different properties, they had different travel times. And importantly, and this is one of the big ideas, and you can see it as part of the title of their model, activation can spread from category and exemplar nodes. So activation in your not your hierarchical structure, activation in your semantic network can spread when nodes get activated. And that spread has very important implications for how we behave. All right, so let's take a look at this. We'll set it up. Let's say that you have the idea of red, right? So we have the concept of red. We know what red is. We know what red looks like. And there are certain things that are associated with red. And in Collins and Loftus's spreading activation model, these would be represented as concepts that are linked to the idea of red. So fire engines are linked to the idea of red. And then there are concepts that are associated with the idea of fire engine. So things like ambulance is associated with fire engine. Vehicle associated with fire engine. Truck is associated with fire engine. Some of those are associated with themselves, as well as with other concepts like car, bus, and street. And then the idea is that some of those connections are going to be, actually, we'll get to that point in just a second. Some of those things are also going to be interconnected as well. So other things that we have connected to red. Well, we have other colors that are connected to red, right? So we got things like orange, yellow, and green. So those are connected to red, even though green is very opposite of what red is. We know that they're both colors, so they'll be connected in sort of that type of a relation. And then orange, yellow, and green would be connected to each other. Red would be connected to the color of certain flowers like roses. And then red would also be connected to different types of fruits that are red, apples and cherries. Those apples and cherries would be connected to other fruits like pears, and then those would be connected to each other as well. And red would also be connected to sunrise and sunset. And then ideas like cloud, which is not anything that's red, but would be associated with sunset and sunrise, would be connected in this network, and then they would have connections among themselves as well. So this was the new idea, that we have these connections, and these connections, they'll have different strengths, they'll have different travel times, and they'll be interconnected in a variety of different ways. All right. So how could we possibly test this? What are one of the implications of how this model works? Well, one of the implications is association priming. And this is the idea that response times are going to be faster if your second item is associated with the first item. So association priming is that idea that if you're thinking about something already, Other items that are associated with that item, you should be faster to react to those other items. So that's the spreading activation in this model. So let's say, for example, we start thinking about red. And I tell you, start thinking about the color red. Imagine the color red. Imagine the reddest color red that you could possibly imagine. Well, all that's doing is activating your red node. So that red node starts getting activated. But this is a spreading activation model. So it doesn't just stay there with the red node, that activation also spreads. And as that activation spreads, other nodes start to get activated. Now, importantly, you might not be thinking about these other nodes quite yet. They might not have reached the level of activation that you need for conscious awareness, but they're more highly activated than they are in their dormant state. And as they get activated, that activation spreads even further from their connections to other connections, and then those other connections get activated as well. So this activation, it's like ripples in a pond. The further away it goes, the lower the activation becomes, but the activation is not zero. It's higher than zero, and it spreads throughout your activation model. So response times are faster if the second item is associated with the first. So we have that idea of that spreading activation. So if you're thinking about red in this model, you are ready to react to fire engine, right? If you're thinking about red is activated 100%. Fire engine gets that spreading activation. It might get to 50%. So it's primed, it's ready. You don't need a lot of effort to bring fire engine into full activation. So in this model, red, I prime you with red, you should be very quick to react to fire engine. In this model, you should be slower if I prime you with red to react to cloud, because cloud is much less activated in this model. And you should be the slowest if I prime you with red and then I ask you to identify street, because street in this model didn't receive any activation. The ripples faded out by the time it got to where street was. So that's the idea. That's the spreading activation model. Let's take a look at this actually happens. And this is what we were doing in our Cog Lab number 10 on lexical decisions. So in Cog Lab number 10, words and non-words were presented. So you saw words like doctor, and you saw non-words like blar. And your task was to determine whether the presented item was a valid word. And you were asked to do this as quickly as possible. So you would see something like speed, and you would say, nope, non-word. You would see something like manner, and you would say, yep, that is a word. And you were trying to do this as quickly as you possibly could. So that was your task. What you may not have known was that the words were actually presented in pairs. And there were 3 conditions for these pairs. So the first was that the pairs made associated words. So the second word was associated with the first word in the pair. The next condition was that they were 2 unassociated words. And then the final condition was that they were 2 non-words. So sometimes you would see associated word pairs. So you would be asked, hey, is doctor a word? And you would say, yep, word. And then your very next word would be a highly associated word like nurse. And then we'd see how quickly you could react to nurse being a word. We had unassociated words, like you would see the word butter. And then the very next word would be thread. Butter and thread have nothing to do with each other. They're both words, but they're not associated. And then finally, the last condition was 2 non-words. So you would see something like speed, and then you would see something like firth, and we would see how long it took you to identify firth, that second word in the pair. All right, so that's the setup. What did we actually do? What actually happened? Well, we have on the x-axis there, type of stimulus relationship. Were they 2 associated words? Were they unassociated words? Or were they non-words? And then we have the reaction time on the y-axis there in milliseconds. And this is the reaction time for the second word. How fast were you at recognizing the second word in this pair as a real word? So not surprisingly, the non-words took the longest to identify as being not a word. And part of this is because they're not part of your semantic network, so it takes longer to search through your semantic network to make sure that something is not a word than it is when you can actually find that word in your semantic network. How fast were we on the unassociated words? Clocked in about 750 milliseconds for that unassociated, unrelated word. So when the second word was unrelated, you took slightly longer to recall that than you did if the second word was related. So the associated words were about low 700 milliseconds for those related words. Now, this doesn't seem like a lot, so let's focus in on that and make it seem like a little bit more. There we go. So this is a significant difference. This is a difference of about 15 to 20 milliseconds long. And one of the important things to remember about research like this is that these milliseconds, when you're talking about cognition, are massive. So 15 milliseconds, 20 milliseconds, when you're talking about the speed of thought, that's a massive difference in terms of how fast you can think about things when you're primed with a related word versus primed with an unrelated word. So the idea here, how does Collins and Loftus's spreading activation model account for faster reaction times for associated versus unassociated words? So why is it that those related words are actually being identified faster than the unrelated words? All right, so just to kind of grease the wheels a little, so it's closer on the branch system. So not only do you have less to travel, we didn't emphasize that part of the model, but it is true that different associations will take different times to travel between each other. So it could be that you need less time to travel there, but it's also part of the reason for it is the fact that that associated word is already somewhat activated. So we're faster on the related words because when we read that first word, it had already activated that second word a little bit. So if that second word needed to get to 100 units for us to recognize it as a word, in the unrelated case, we brought it from 0 all the way up to 100, and that takes a certain amount of time. In the related case, that first word already spread its activation to that second word. So it might have been at 50. We weren't thinking about it, but it was at 50, and going from 50 to 100 takes a lot less time. So it's the idea that the related words were already activated somewhat. So to get them to the point where we can make a decision required less time because it required less additional activation to get them to that position. All right. So that is kind of the theoretical implication of this. Let's take a look at a real world implication. So what implication does this spreading activation model have for global warming as a term? Okay, so awesome point. So we have the word warming in here. There's a lot of different things that are going on with climate change. It's not just about the earth getting hotter, although that is a big issue. It's not just about that. But again, that warming would spread its activation to all these things associated with heat, with getting warmer, with increasing temperature, and those would be activated, and you would more likely be thinking of those, and your mind would more likely wander to those ideas and then not see the associations or not as readily think about other things like species dying and weather patterns changing, the salinity of the ocean, changing, all of those other things. What about the term global warming as a term? Is it effective or is it ineffective? So it does put it under a big blanket term. Blanket terms are not necessarily bad because they help us kind of organize and simplify things. But what do you think about? Let me try this. What do you think about when you think of the term warm? Let's break it down. Not so much warming. What do you think about warm? Does warm fill you with positive thoughts or does warm fill you with negative thoughts? Positive thoughts, right? So warm kind of, you think about things like warm cookies. You think about your favorite sweater. You think about coming home, on a cold winter's night and getting under the blankets. And ooh, I feel so warm. Global is also typically not associated with negative things, right? Global is typically associated with positive ideas. So this is not my idea in terms of is global warming horrible as a term. This actually came from Seth Godin. And Seth Godin, if you are looking to kind of take your production and impact in the world up a level, I highly, highly recommend Seth Godin. He was one of the people that turned me around and made me able to publish a lot of the work that had been sitting on the shelf. But he brought up the idea that global warming is a horrible, horrible term because in Loftus's Colin and Loftus's spreading activation model, what happens is that you hear the word global and you hear the word warming, and it sends out that activation. But before climate change was an issue, when this was, 10, 15 years ago, before people really became aware of what was going on, and the term global warming was introduced, the associations, the emotional associations with global were things like hope and curiosity, right? You don't want to be isolated. You want to be global, right? You don't want to not have experiences. You want to go out. You want to see the world. You want to be global, right? Things like compassion, worrying about your fellow man. Let's think globally. Act locally, but think, globally. Things like inspiration, things like empowerment, things like pride in the human race. Global is associated with many, many positive ideas. You can even just think of the term Mother Earth or Mother Nature, right? Mother is associated with Earth. Mother is associated with many, many positive things for many, many people. So again, we have this idea that global now is priming all these positive ideas. What about warming? Like I said before, warming is great. Who doesn't like warm cookies? Who doesn't like a warm sweater? Who doesn't like to come in out of the cold and feel warm? Who doesn't like a warm hug, right? Nobody's ever like, oh man, I could go for a cold hug right now, right? It's always like warming is associated with positive things. So things like comfort, things like affection, things like love, things like trust, things like happiness, things like gratitude. Those are all the terms that are primed when people said global warming. So they said global, and you're like, oh, wow, great. It's global, right? Empowerment, inspiration, wonderful. And then they followed it up with warming, and you're like, awesome, comfort, affection, love. Who doesn't want global warming? It's like giving the earth a big hug. That's what the term prime. So the fact that it didn't really have that kind of an impact that it needed to have is not surprising. Because again, there's not these negative ideas associated with global and not those negative ideas associated with warning. So Seth Godin came up with the idea that what we should have called this and what would have gotten a better reaction would have been not global warming, but something like atmosphere cancer. And if you went to anybody and you said, hey, what do you think of atmosphere cancer? Well, they're not going to say, I'm kind of curious about it and I'm a little bit inspired. And yeah, I'm very comfortable and I feel gratitude. No, they would be like, oh my gosh, well, I don't think much of atmosphere, but I know what cancer is, and that has activated fear, and that has activated anxiety, and that has activated sadness, that has activated shock, and that has activated anger. And also on the positive side, that has activated determination, right? So that would have been a much more effective term for this idea of global warming. If they called it atmosphere cancer, it would have been a lot more impactful and a lot easier to push people towards the correct way of thinking about this, saying, look, we got to get angry about this, we got to get worried about this, and we can also get determined about this. And all of that would have come with the term on its own, activating your spreading activation model, if we had called it something like atmosphere cancer. All right, so that's what I wanted to talk about, the global warming as a term. What I'm going to leave you with, just an idea, because we are going to pick up one last time with spreading activation. What implications does this model, think about this for the next time we meet, what implications does this model have for stereotypes, have for racism, have for sexism? And think about this in terms of not only the spreading activation model, but also remember the memory suffix effect that we were taking a look at when you were remembering digits in a row and the cue was either a beep or a zero. Remember how ineffective you were at not remembering the zero. And we'll talk all about that next time we meet. Yep. All right. So that is it for today. See y'all next time.